You wouldn't think, superficially, that there was a big secret to LEDs, but there kind of is, and it's not a conspiracy or anything, but most people don't understand how LEDs work. One of the fundamental flaws of the scientific method is not the invention or the discovery or the tinkering and the invention thereof of all sorts of fascinating things, is that the invention and discovery of things has no connection whatsoever to the explanation of how that discovery works. Now, most people know that incandescent light bulbs, for example, not only suck a lot of energy, but they generate a lot of heat for the luminal emission. Of course, light is not emitted for anything. It's an ether perturbation. Light doesn't propagate from point A to point B. Light is not a wave. Light is not a particle. All the fundamental things that current science believes it understands about light is incorrect, but that's not really pertinent to the discussion of LEDs. We're going to explain LEDs here really briefly. Of course, all current technology that humans have, coal, nuclear, so on and so forth, is based upon explosion technology. And of course, the revolution of power generation is going to be in implosion technology, because right now what we're talking about is explosion or centrifugal divergence, the burning of energy, fossil fuels, so on and so forth, nuclear and whatnot. LEDs are extremely close to implosion technology. Of course, LEDs absolutely, of course, require power, but they don't require much power. And everybody knows that LEDs emit a lot of lights, and they run pretty damn cool, and they don't require that much power. But what's the secret of LEDs? Let's actually explain LEDs accurately from a person that actually understands field theory and what's going on LEDs. Let's actually eliminate this. What we're looking at, and by the way, let's first start off by, before we go very deeply into LEDs, it's generally and widely known that LEDs are bad for your eyes as opposed to incandescents, but nobody knows the reason for that. The reason for that, and a lot of people think that laser light is a coherent illumination, but that's only an attribute. What laser light is specifically is point source light, and the reason why LEDs are bad for your eyes is because, like a laser, it's point source light. While it is incoherent light, it is still point source light. That's why LEDs are bad for your eyes. Everybody's going to that to save energy, but what they're doing is they're ruining their eyes. Anyway, let's get on to the semiconductor materials. In semiconductor diodes, we got P-type and N-type. Over here we have P-type. Whoops. Excuse me, over here we have P-type, and over here we have N-type. Specifically, all this really means is we have a positive type, which is unbelievably, you can't believe what science actually calls this. They call this whole energy. You can look it up, energy, whole energy, as if there's little holes over here. They literally think that there's like missing holes, like a hole in a whack-a-mole over on the P-type. What they are actually charge disparities on the P-type. P-type are positive, and the N-type are negative, but the N-type are not exactly negative. They're electrostatic. So we got positive here and negative over here. But the semiconductor diodes are doped in the case of P-type. Let's do silicon here on the P-type and silicon over here. On the P-type, the silicon semiconductors are actually doped with boron, okay? Which actually means it's in the material itself, okay? Boron. And on the silicon side, the N-type are doped with phosphorus, but what they are is electrostatically charged, okay? Phosphorus, okay? So we have P-type and N-type. And here we're going to put ourselves a little battery, because that's almost all it takes to power, right? A LED. Yeah, actually I drew the wrong thing over here. Eraser, there we go. Okay, negative sign. We're gonna hook up this, and this is the P-type boron doped semiconductor. For the silicon semiconductor in the case of our LED. What we actually have here in the center is counterspace, right here, right in the middle of this neat little zone right here, technically, is counterspace. But what scientists call this is the depletion zone. By the way, to get visible light, we need to use gallium arsenide or gallium phosphide for red, green, and orange and yellow colors, and we use high-energy gallium nitride for blue light emission, but let's not go too far into that. But here, what we have is our LED right here, okay? When placed next to each other, they discharge their electrostatic charge into counterspace. Because like charges repel, right? Negative here, positive here, positive here. What they do, let me actually erase this out right here and redraw in. Okay, what they do is they mutually move towards counterspace, and the electronegative, because when placed next to each other, they actually discharge their electrostatic charge in the counterspace, which causes an ether perturbation, therefore the release of light at a given frequency, whether that be gallium arsenide or gallium phosphide or gallium nitride for visible blue light. And of course we have infrared, and of course the really powerful lasers, which don't require much energy, like a 5-watt very dangerous blue laser, which is also an LED laser, uses a battery that's about 3 times the size of a AA battery, and to get a 5-watt blue, extremely dangerous blue laser emission off a battery so small shows you the power, not only of point source light, but the minimal amount of power, which is almost the closest thing to implosion technology, and it does require power. And of course, a battery, of course, is charged by something. You charge up a battery with nuclear or coal or wind or solar, whatever you charge the battery with. So it's obviously not zero energy. We're not talking about free energy here. LEDs require energy, but they don't require that much energy relative to an incandescent light. But adding power to these proximal p-type and n-type semiconductors forces the charges to dissipate into counterspace, which causes the manifestation of this neat little stuff called light. Yeah? Doesn't require that much energy. When you actually use an electronegative, which is an electrostatic, actually. This is an electrostatic. Don't write up there. Electrostatic, and this is a discharge on the positive, which is boron doped. They actually move towards each other and dissipate in what science calls this little region right here, the depletion zone, but it's really counterspace. When a battery or power is connected, the central depletion zone actually shrinks. The depletion zone actually gets infinitely smaller. You're actually creating a point here by which the charge disparity between the electrostatic is not negative. The electrostatic, it's electrostatically negative, but I mean, we're not talking about a charge-carrying particle or an electron here. I mean, Nikola Tesla said there's no such thing as a charge-carrying particle or electron. Even the discoverer of same, J.J. Thomson, denied that for a long, long time until he was offered a Nobel Prize for same. Also, to Oliver Heaviside, there's no such thing as a charge-carrying particle. We're not talking about electrons here. We can think of electrostatics in the term of lightning, if you want to make it analogously very simple. But when a battery is connected, the central depletion zone, or counterspace, the smaller the space, the higher the capacitance, by the way, shrinks to where these dual inversely charged doped semiconductors, p-type and n-type, dump their charges into counterspace, but in so doing, they release light, and they don't require that damn much power. Have you ever seen how insanely small, like a ultra high, I mean, one that will literally light up downtown? You could hold it in your hand, and it runs off of 3 123 batteries. You've seen some of the really expensive, ultra high quality LEDs that will literally light up downtown. They're as bright as a old time searchlight or spotlight. Well, those World War II spotlights is like about 4 feet wide, and it took like a generator to power the sucker. Well, these run off of 2 123 batteries, and they're just as powerful. All atoms are nothing, of course, other than electric dynamos. When their charges are dissipatively forced into counterspace, into the boron-doped p-type semiconductor, they lose their energy and they create light. They cause an ether perturbation of EMR at a given frequency. Now, choosing the frequency depends on what you dope these silicon semiconductors with. Gallium arsenide, gallium phosphide, gallium nitride for blue light, which is really powerful, which they also use those for blue lasers. So, this is fundamentally no different, and you can see lectures of this from Eric Dollard who said that the lightning, he's not the only one that said that, he didn't actually come up with that. He said that lightning is nothing other than a discharge into counterspace, and he's correct. So an LED is technically nothing more than a micro lighting device. Let me see, go to erasing here, and back to our pencil. So we got our P-type and our N-type, yeah. It's not really a negative charge. Like I said, and we hook up our little battery here. Yep. Positive and negative. Right here. And when you actually hook that up, you actually cause a charge disparity, and you change the nature, the depletion zone before the battery is turned on, or the charge is attached to the two, and they are directly against one another, the P-type and N-type semiconductor, boron or phosphorus doped, or gallium arsenide or gallium phosphide, yada yada. The depletion zone goes from this, and once you turn the battery on vis-a-vis a switch, the depletion zone goes from that to basically nothing, and then the charges dissipate into counterspace. This is why LEDs don't require that much power. LEDs are literally, and I mean this very, very literally, LEDs are nothing more than micro-powered lightning devices. Do you know what lightning actually is? It's a discharge in counterspace between ground. The P-type is a ground. That's all a P-type is. It's a ground, and these are the electrostatically charged phosphorus-doped negative. They call it N-type. They call it N-type, but that just means negative type. There we go, a negative type. But the P-type is a ground, and they just dissipate into counterspace. Both of these are silicon semiconductors, are just doped with different materials, such that the charge disparity would, and it's amazing that science calls this the depletion zone right here. The depletion zone. Right. No, it's counterspace. This is effing counterspace, for God's sakes. That is actually how an LED works. The scientific method is fundamentally flawed at its most fundamental level. Sounds, did I use the word fundamental twice there? In that its discoveries and its inventions are not connected, nor are they directly rationally explicative of the descriptions that they use or the explanations they attempt to use to define their discoveries or their inventions. Inventions and discoveries are not directly relational to correct explanations of how a phenomena or an invention actually works. But that is what an LED is. That is why LEDs can emit enormous amounts of power with enormous amounts of light, enormous amounts of light with extremely little power. LEDs are amazing. Have you ever seen how tiny an LED is on an ultra bright, I mean, so blinding it will hurt your eyes. Really, really, really bright. I mean, like 10,000, 20,000 lumen LED. I mean, the little LED is about, like a 10,000 lumen LED from like Surefire. I think the actual surface area is like 2 millimeters by 2 millimeters. It's about like that. This little 2 millimeter LED is emitting as much freaking light, or lux, or lumens. I don't know if you've ever seen them, like the old Hollywood movies where they'd actually have those enormous, and I used to have one way back in the day, my family did. I mean, it was 5 feet across, it required a generator the size of a freaking car, or you could hook it up to a car. You know, the spotlights. Remember those huge spotlights? Sucker weighed about 500 pounds, yeah? And now we've got something that's 2 millimeters by 2. This required an enormous amount of power. This requires a battery. And it's emitting as much or more light than the freaking Hollywood spotlight, analogously. That is amazing. I have one of these, by the way. It's rather expensive, and it's insanely powerful. It does generate heat, because Well, you can get into that. That'll take a little while longer. It doesn't generate that much heat relative to anything else, though. I mean, these things get so hot you can, literally fry yourself on them. These just get hot to the touch, where they'll, slightly burn you if you were to touch the heat sink that's connected around the LED, because light is energy. It generates heat, but it's not lossy. In other words, the energy isn't lost in the heat itself. It's in the generation of light, heating up the surrounding matrix and material and lenses and magnesium chassis of the actual LED flashlight itself. But anyway, there's the fundamental secret of the LED in a nutshell. Thank you so much.